when we do that multiplication, and we're not going to cross out because that's not real math, what does that second term simplify to? 2v divided by r. The pi divided by pi is 1, and you have r divided by r squared is 1 divided by r. All right, now, remember, what is v? Constant. V is a constant, so we're not going to use the quotient rule on that because we don't want to overcomplicate. The differentiation is supposed to be the hardest part. So we don't want to do anything that makes the hardest part even harder. We don't want to do anything that makes any part even harder. All right, what should we do right now? What do we need to do? Done it every single problem. Louder, John.
Find the domain.
We have to state the feasible domain. Okay, that is a common student error, is just to blow through that part and skip it. Okay, because domain wasn't a big enough part of your prior studies. It is an essential part here. So that's going to be, you think, oh, that's -1. No, it's not. Okay, that's going to be a more minimum 20%. Okay, because it's going to affect a lot of other things in a problem. All right, so we have to look at minimum and or maximum values of r and whether those values are included or excluded. And remember, those are always based on two things, based on the function and it's based on the context of the problem. So let's first, and I always do it this way, I always look for a minimum value first and then I look for a maximum value. All right, minimum value for r. What? All right, inclusive or exclusive? Exclusive. Okay, r has to be greater than 0. Remember, this is something that we're looking to build in theory. You can think of this as an engineer, packaging engineer is looking to design a can. So it uses the minimum amount of metal. Things that exist in the real world have to have positive dimensions. Otherwise, you can't build them. So r has to be greater than 0. If r is equal to 0, how much stuff can you put in your can? Nothing, and it's completely useless. You can't even make a can with a radius of 0. All right, so r has to be greater than 0. Now, let's look for a maximum value. All right, we had related discussion yesterday in class. There is no maximum value. For the same reason that we didn't have a maximum value with the crate problem. And to reinforce that, because this is important, if we look here, we're going to see what happens if we keep making r larger. Because remember, h has to stay positive also. Because if h isn't positive, we can't make a can. All right. If we keep making r larger, if we take its limit as r goes to infinity, this quotient, where does this quotient go? It goes to 0. Okay? Does it ever become 0? No. That's why there's no upper limit. Okay? So that's something that you could do. I don't need to see you write down the limit as r goes to infinity, but it's something that you have to think about. All right? So r is strictly greater than 0, no upper limit. Now remember yesterday we talked about making that crate that was like 1 billion meters by 1 billion meters, having that infinitesimally short height? Okay, obviously not practical, but we could do the same thing here. We could make r equal to 1 billion whatever, so there's no unit given, and that's just going to take the h and drive it closer to 0. So that can is not practical at all, because you can't put it in a store, can't put it on a shelf, can't put it in your cupboard, can't put it in the fridge, and it would take you an incredibly long time just to open the can. Can opener and going around, all right? Even if it was a pop top, being able to pop it and pull something off that's that large, right? The force that you need to apply. All right, now what do we do next? Take the derivative, okay? And don't overcomplicate it. What do we know about 2 pi? Constant. So do we use the product rule there or no? No. No. That's overcomplicated. What's the derivative of 2 pi r squared with respect to r? 4 pi r. Okay, now we want the derivative of 2v divided by r, and since v is a constant, we don't use the quotient rule. So what's the derivative of 2v divided by r?
-2v over r squared.
Negative 2v divided by r squared. Because we're going to rewrite 2v divided by r as 2v times r to the negative first, differentiate using the power rule, negative 2v r to the negative second, subtract 1, and then we rewrite it. All right, so that should be, by now, mental math. It's just like, if you learn how to add in first grade, by the time you're in second grade, you shouldn't have to do any drawings to why 3 plus 5 is 8. That you have 3 of these in this pile, and then you have 5 of these in that pile, and then you got a pile underneath it with 8 of them, and that's why 3 plus 5 is 8. Okay? You don't need to do that when you're in second grade because you understand it by then. All right, what's the next thing that we need to do? Set it equal to 0. Have we been consistent with these patterns? Do this, then do this? Yes. It's just that what we're doing it with is different from problem to problem. Okay, what are we solving this for? R. We don't solve for V because V is a constant. We solve for R. So this part is algebra. I'm going to reduce that to V divided by 2 pi. And then what do we need to do to each side? Cube root. We had people yesterday taking square roots. Right? That's no good. All right, the cube root of r cubed is not the absolute value of r. It's just r. Because there's no such thing as a principal odd root and a negative odd root. There's just the odd root. You need absolute values when you're doing an even root of an even power. This is an odd root of an odd power. Cube root of v divided by 2 pi. Okay, so that's our critical value. We don't have any included endpoints. And remember, what value of r will make this derivative undefined? 0. Is that in the domain? No, and that's consistent with what we've been talking about, because this can exist in the real world, and our real world is a defined world. So the values that make the derivative undefined are generally not going to be in the feasible domain. So they've already been ruled out of the discussion. All right, now, we need to justify this, because there's nothing that says that this is that this produces a minimum surface area. So what we've been doing is Plan A, our first derivative sign test for justification. That's not practical here. Right? What would make a first derivative sign test difficult here? We don't know what v is. So if you say, well, I'm going to pick 1 in that first interval. Well, how do you know if 1 is in that first interval if you don't know what v is? Okay, so that really rules out the first derivative sign test. But that's still going to be Plan A. We're going to look at a different way that we can justify this as our answer when we have situations like that where the sign test isn't practical. All right, so what we're doing is a Plan B. And we look to use Plan A first. That's the names. You don't look to use Plan B before Plan A. We're going to do something called the second derivative test for extrema. This is used sparingly because it is some extra work. And as its name would imply, what do you think we need to find? Second derivative, thus the name. So it introduces a second line of calculus into the problem. Right, and the only time you need a second derivative is if you're going to use a second derivative test for extrema. Right. Sign test, Plan A, second derivative test. This is not a second derivative sign test. This is something different. So this is something new that we haven't looked at before. So we need to find S double prime of R. All right, so just going to differentiate term by term. What's the derivative of 4 pi r with respect to R? 4 pi. Okay, and then we want the derivative of negative 2v divided by r squared with respect to r.
4v over r cubed.
4v divided by r cubed. Again, rewrite it with a negative exponent. Negative 2v times r to the negative second. Use the power rule and then rewrite it. I don't need to see the work. All right, now the next thing that we're going to do is we're going to take that critical value that we just found, the cube root of v divided by 2 pi, and we're going to substitute it into the second derivative. And so I have to substitute that. It's not as bad as it looks, because what are we going to be able to do with that value? Cube. We're going to cube the cube root. All right, and that's going to make it a lot easier to work with. Okay, now you need to be able to simplify that second term. Okay? Without guessing, what does it simplify to? Just the second term. 4v divided by v divided by 2 pi. 8 pi. Remember, what are winners going to do to simplify that? Multiply by the reciprocal of the denominator. 4 pi times, or 4v divided by v divided by 2 pi is the same as 4v times 2 pi divided by v. So we can add them, that's 12 pi. The most important thing is we need to know whether that value is positive or negative. It's quite obviously positive. All right, that's the essential thing, is knowing whether that works out to be a positive or negative value. The value itself doesn't affect what we're going to do. All right, now we're going to draw some conclusions. Now, what is S prime equal to at that value? Without doing any substitutions, what is S prime of our critical value equal to? John? 0. Because think about, how did we find r equals the cube root of v divided by 2 pi? Set what equal to 0? S prime. We set S prime equal to 0, and we got that r value, so S prime at that r value is equal to 0. Now, we're going to make an interpretation based on that one piece of information and nothing else. Absolutely nothing else. There's only one thing that we could say with 100% certainty about S. So, when I say 100% certainty, if your answer involves might have or could have, that's not 100% certainty. So the only thing that we could say about the graph of S with 100% certainty, based on the fact that S prime is equal to 0,
Non-zero.
and also without guessing, the fact that S prime is equal to 0. Because it's at a point. S prime at that point is equal to 0. What's going on at that point? Can't say that there's an extreme value. There doesn't have to be. That's a might have. You start off all right. Wow.
I mean, that's
We're recording that.
so the first time in 17 years.
Yeah.
That's like two long.
All right, can we rewind and, oh, we can't pretend that didn't happen. Can we get back on track? Oh, that, you're just restating what that is.